This is a vivid training on the Above-Anvil Cirrus plume, which you can use as an indicator of severe storms in visible and infrared satellite imagery. I'm Scott Lindstrom from SIMS. Chauncey Schultz is the Sioux at Bismarck, North Dakota, and he has viewed AACPs with severe weather during the warm season there. Chris Bedka is one of the world leaders in research into AACPs and their relationship to severe weather. This is an animation from GOES 14, so an oldie but a goodie, of visible imagery, storm-centered, that shows the development of a strong and isolated thunderstorm. The advantage of identifying the above-anvil cirrus plume is that it is associated with severe thunderstorms. In the absence of other observations, radar for example, this can help you know where severe weather might be occurring. In concert with the radar, it can give you extra confidence in warning issuance. So I hope you've picked out the above-anvil cirrus plume that forms near the end of this animation. It's pretty noticeable. What do I mean by an above-anvil cirrus plume? That's highlighted in this image. It's that smoky-looking cirrus plume. An AACP can be in the stratosphere, which means it'll be warmer than the cloud underneath it. It can be very thin, which means radiance from underneath might leak through. All of this makes it sometimes difficult to see the AACP in infrared imagery. Recognize that an AACP might be warmer if it's in the stratosphere, or colder if it's in the troposphere at cloud top. Investigations of AACPs have used a multi-instrument approach. Radar imagery tracks the storm and is combined with multispectral ABI data, radar imagery of storm rotation, updraft and microphysical data, Earth Network's total lightning, severe weather reports, and National Weather Service watches and warnings where appropriate to identify severe storms and to analyze the AACP signature. The observations are taken at very high temporal resolution. So this is a complicated figure, but it's showing you all of the different ways that you can observe an AACP and link it to a severe storm. AACPs correlate very well with strong updrafts, with wave breaking in and ice injection into the stratosphere or upper troposphere. Plumes are a warm anomaly if the atmospheric thermal structure is well behaved. That is, if there's a well-defined tropopause with a warmer stratosphere above. You can find examples of cold AACPs, however, so be aware of that. As noted, a plume can be relatively easy to find in visible imagery, especially when the sun is low in the sky. The cirrus plume is thin, and infrared imagery can therefore penetrate through from below, diluting the warm signal. The warm signal should originate from near the overshooting top. It's a very strong updraft that punches through the tropopause, causing the wave breaking. Here is an animation from 23 to 2312 UTC of a strong storm over North Dakota that shows what a plume looks like in visible imagery in the bottom left, in the sandwich product right above that, and in two different infrared IR enhancements. Those are on the right. Don't be afraid to tweak the enhancement to view the plume if you think it's present, because its presence should make you more bullish on warning issuance. This still image from 2312 UTC includes a blue arrow that's pointing toward the AACP. Now let's jump ahead an hour. This is from 0 to 12 UTC. The AACP at the southern end of the cell continues to expand. Here's another example of an AACP from 2018, at a time when stereoscopic imagery could be used to view the storm, as noted in the link to webpage on the SIMS satellite blog. This slide annotates where the AACP on the previous slide exists, and it includes the infrared imagery. In this example, I find the plume much easier to view in the visible than in the infrared. But if I were to go into AWIPS and tweak the infrared enhancement, the plume might stand out a little bit more. So here's another try at an enhancement. Scott Bachmeyer at Sims is the one who's provided these infrared images. Maybe it shows up a little bit better in this one. This shows calliope measurements across a plume from a different storm than the one we just viewed. Note that the plume is between the two arms of the enhanced V and downwind of the overshooting top that is the vertex of the enhanced V. The region between the two very red arms of the enhanced V is a cloud that is much higher than in the adjacent regions. That's what E is in the image on the upper right. This is the AACP, and the image on top shows the cloud protrusion in between the arms of the enhanced V. AACPs are relatively easier to find in visible imagery, as I've said. If you just have a single infrared imagery, it can be tough to view the AACP, and animations might make it somewhat easier. Or you might, as I've mentioned, adjust the infrared enhancement. That might be a challenge if these AACPs are in your CWA, but if it's a quiet night and AACPs are happening elsewhere, take some time to experiment. This is an excellent example of multiple severe storms and multiple plumes over the high plains. Visible imagery on the left, infrared imagery on the right. I claim the plumes are easier to view in the visible, but experienced plume finders might find them in the infrared as well. Here are the warning polygons. They are under the storms with plumes. And observed severe weather also occurred near plumes. Remember, plumes can be warmer than the enhanced Vs. Key on that when you examine the infrared imagery. Scientific study on plumes and the relationship with severe weather required plume identification. This slide describes the methodology and how the identified plumes correlated with observed severe weather. Note that 10% of the storms in this study I'll be talking about produced plumes. So 405 plume-producing storms and 4,100 non-plume producing storms, with the data sources shown at the bottom. How were the plumes identified in the study? Examples are listed on this slide. You've heard some of this information already. Plumes can be warm, but some tropopause structures can lead to cold AACPs. Note that the plumes were identified by two different people, and they usually agreed. This figure shows why plume identification is important. Look at the black lines in these slides, showing the paths of storm tracks with plumes, compared to the white lines, which are storm tracks with no plumes. Then look at the overlay of severe weather events. Wind, hail, and tornadoes occur far more frequently on top of the black lines, which are the plumed storms, than on top of the white lines, which are non-plumed storms. Severe reports cluster along the black lines that show where the plume storms were moving. Indeed, plume storms produced 14 times as many severe events as non-plume storms. 3/4 of all supercells generated plumes. 59% of the plume storms were severe. 73% of the storms producing large hail, strong gusts, or tornadoes had plumes. The takeaway is use the presence of a plume to boost your confidence for warning issuance. That's especially true if you're in a region of poor radar coverage. You want to use as much information as possible in your warning decision. The presence of a plume is one more powerful piece of pro-severe information. You're now looking at infrared and visible imagery of a plume-producing severe weather event over North Dakota. Here, we're looking at imagery from 0031 to 0123. The presence of a plume should boost your confidence in issuing warnings, and maybe also for tagging the warning with higher gusts or higher hail sizes than you might otherwise consider given radar alone. A warning here was issued at 124 UTC, just after the end of this animation. What in the satellite imagery convinces you that a warning might be issued? So here's an image at the time of warning issuance. Can you view the multiple plumes? There's also a great enhanced V in there as well. The satellite imagery continues here from 123 to 149 UTC. Does the observation of 3.5-inch hail at 149 UTC surprise you? Note in particular the very cold cloud top. Here's the still image at 149 UTC. This animation goes from 151 to 213 UTC. How do you think the storm is evolving? I'm noticing some warming of the cloud tops. Now we're going to look at some radar imagery with this storm. The difficulty here was that it was some distance from the radar, so the low-level structure of the storm was very difficult to sample. This screen shows what you'll be seeing in the next animations. We'll be looking at the easternmost storm. That's this one. It's going to split, so focus on the southern one, not the northern. So this is the part of the storm we'll be focusing on, and it's pretty far from the radar at MBX. This animation is every 2 minutes from 36 to 0124 UTC. That's also the same time as the first satellite imagery animation that you've already seen. Note at once that the eastern cell splits. It's hard to see a specific signature in the radar, though, to pull a warning trigger, but one was issued at the end of this animation. Here's a still image of the radar at the warning issuance. So the warning was issued, 1/4-inch hail and 60-mile-per-hour winds. And here's what the satellite imagery looked like at the same time. There's a significant parallax shift between the coldest cloud tops, suggested by the visible imagery being so bubbly, and the radar presentation of the storm. It's in a whole different county. The animation continues here from 126 to 138, at which time the tag on the storm was increased to 1.5-inch hail and 60-mile-per-hour winds. And the satellite imagery is part of this animation too. Note the continued presence of the AACP. Here's the still image of the radar at the time of the tag increase. With the satellite still here as well, the continued AACP is obvious, and so is the parallax shift. We're going to continue the animation from 138 to 152. That includes when the 3.5-inch hail occurred. And here's the animation from 152 to 212 UTC. So that cell is moving pretty far away from the radar at this time. But in this case, the AACP was vital to helping understand that there's likely severe weather happening with this distant radar cell. And MCS can also generate plumes, and the relationship between plumes and observed severe weather remains. How does the presence of an AACP relate to lead time in a warning? That's shown in the figure on the left. The black line shows the appearance of an AACP. The red line shows the time of the first warning. AACP often showed up about 0 to 10 minutes before the warning issuance. So if you're itching to pull the trigger, maybe the presence of an AACP should help. Especially if you don't have radar coverage, consider forefronting the presence of an AACP as something in your checkmark list of what has to happen before warning for severe weather. The next series of figures show box and whisker plots that show the relationship of the 40 dBz ecotop height to the tropopause height and whether or not a plume is present. A plumed storm is more likely to have 40 dBz near the tropopause. That's because it has a strong updraft. So the 40 dBz is where there's heavy ice and liquid precip, graupel, and or large hail. And across the bottom, we have no plumes with non-severe storms, no plumes with severe storms, storms before plume forms, plumes with non-severe storms, plumed severe storms, and plumes no longer being generated. So compare, for example, the box and whisker plot on the left for no plume non-severe, and the box and whisker plot almost on the right where we during a plumed severe storm. There's a similar relationship with next-rad divergence. Both of these means that large ice particles will rise higher into storms with plumes relative to non-plume storms, and that's especially true if you have severe storms. So the height of large ice particles is about 2.5 kilometers higher, and the outflow rate has increased by about 50% for plume storms. So think about what that's meaning for the storm dynamics. But if you look at the minimum infrared temperature, you don't really see the same discrimination between plume and non-plume storms. Both non-severe and severe storms can have very cold infrared temperatures. So really, you don't want to use just cold temperatures alone to identify a severe storm. If you want to read more about this, there's a weather and forecasting paper on it. There are some blog posts down at the bottom. I'll add these links into the YouTube as well. A summary slide. On average, cloud tops are highest and updrafts are most intense when an AACP is being produced. AACP storms are more often severe than storms without plumes. Also, AACP storms generate the majority of significant severe weather events, so almost 3/4 of them. And by that I mean storms with 2+ inch hail or EF2+ tornadoes. Plumes appear about 31 minutes in advance of the first severe weather report on average. So if you're keying on plumes, you might be able to issue your warnings a little bit earlier. Storms without plumes will often generate severe weather. But a plume is better correlated with severe weather than just about any other known GOES visible or infrared cloud top signature. I think that's a pretty powerful takeaway. That's from Chris Bedka. That's all I have. Thanks for listening.